The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Welcome back from this short break. Remember, by now we know a little bit about how lasers work. We know how light amplification comes about. Excuse me. We even know how a laser starts. Now let's look at what causes the bandwidth of the laser. Okay? And what does that bring with it? What sort of properties of lasers will come with it? So here it is. We have the bandwidth of the amplifier, which is really the tuning range of the laser. So let me remind you that we're dealing now with essentially a three-level system where there's a pump that's creating a population inversion between the 3 and 2 levels. And as we've shown before, we get gain at this frequency, at this 3 to 2 frequency. And the amount of gain depends, again, on some constants, but the key thing is the population difference. And the width then depends on what? And that's what we want to find out in this section. Well, the width here is determined by all sorts of things. One is the fact that there is spontaneous emission. As you know, when when atoms decay, they radiate an exponential waveform, and that, just like we showed before, has a width. So if that was the dominant effect, then the whole width would be essentially the effect of spontaneous emission. But in, say, something like a gas, we have collisions, and collisions can effectively shorten this transition time, this decay time, and essentially will broaden the width. And also the Doppler effect, because atoms are moving, there is, as we're all familiar with the Doppler shift in the frequencies, again, that can cause broadening. So this width here can be quite complicated. It could be made up for gases, it could be made up from spontaneous emission, collisions, Doppler, and what have you. And for solids, for solid amplifiers, they have other broadening sources. So basically, this is not a trivial width here, but it can be measured and then can be attributed to all sorts of effects. Now I see that we have a phone call, so let's take this phone call right now.
Dr. Ezekiel, one quick question.
Can you be a little louder, please?
Yes, one quick question regarding the pump.
Where are you calling from, by the way?
Hartford Graduate Center.
Hartford?
Yes.
Uh-huh.
One quick question regarding the pump.
Yes.
Could you just explain how that starts? If we were to look at the pump schematically, is that some high voltage being applied, exciting those electrons?
Oh, well, I tell you what, so far I just wanted to indicate that there is a pump. If you can wait just a little bit, I'm going to show you, when I discuss the variety of lasers that they are, and show you what the pump is in each case. Like in some cases, it's going to be a light beam. In some cases, will be collisions. In some cases, it'll be electrons colliding with something. And in the case of the helium-neon, it'll be helium colliding with neon. So if you just wait a little bit and see how that goes, and then can get back to me if I'm not clear. Okay?
Okay. Thank you very much.
Good. All right. So, and I encourage you to ask questions anytime. So then the width of just to summarize, then the width of the laser amplifier then is, as I say, is made up of all sorts of things, and of course it depends on which is the dominant one. If there isn't if the collision is not the dominant one, maybe the Doppler is, or if the Doppler is not dominant, maybe the spontaneous emission lifetime is, and so on. But in any case, we're going to have a certain width. And now let's see what can happen because we have this width. All right. So in fact, this is the width that determines actually the spectrum of laser light. All right. So let's then do a little review here. We said before that what I've drawn here, here's the amplifier. Here's the bandwidth of the amplifier. Here are the modes of the resonator. And here in dotted, I've drawn what I call the loss line, which is made up of 1 minus R, 1 minus reflectivity, which is then equal to the transmission of the mirror plus the absorption in the mirror A. But whatever it is, that's the loss line. This is the loss that the gain has to overcome before you get oscillation over here. So in this situation, the gain is below the loss line and no lasing occurs. All right. So the first thing we have to do in order to lase, then we have to increase the gain, the amplifier, above the loss line. In this particular case, there's one cavity mode here, and as we mentioned before, then the gain here is bigger than the loss at this value, so therefore the laser will oscillate, spontaneous emission will start it off, and the output, you get this delta function output. All right, that's what we call is a single frequency laser. All right, now when we have more modes under the gain curve, like over here, in this particular case, the cavity spacing, remember, it depends on the length of the cavity, so the longer the cavity, the closer the spacings are, because C over 2L is the separation. So in this particular case, I show 3 modes under the gain curve. Now, even at this mode here, there's enough gain to overcome the loss, because this is the loss line. So in a way, I'll get 3 laser frequencies oscillating. And of course, if the bandwidth of the amplifier were bigger, then I would get even more frequencies oscillating. Now, again, if you don't believe me, we have a nice little demonstration for you. All right, a demonstration that is based on the spectrum of laser light. You know, so the idea here is to have a way of examining this spectrum using what we call a scanning Fabry-Perot cavity or a high-resolution spectrometer, and that will tell you whether the laser is oscillating in 1 or 2 or 3 or more modes, and so on. So now let's look at this demonstration on the spectrum of laser light. The spectrum of laser light. For example, is the spectrum, is it a single frequency, or is it multiple frequency, or what have you? In fact, we're going to look at the spectrum of light from 2 lasers, 2 helium neon lasers. We have this laser here with external mirrors, and the one over here with internal mirrors. And the way we're going to look at the spectrum is by using the optical spectrum analyzer here. So now let me turn on this laser with external mirrors, and the light from the laser then is reflected by this mirror, and here it is going right into this optical spectrum analyzer, which is a scanning Fabry-Perot cavity. The output of this spectrum analyzer then goes to an oscilloscope over there. As we can see on the oscilloscope, we have more than one frequency. In fact, we have several frequencies, sometimes 3 and sometimes even 4. The spacing of the modes here is about 270 megahertz, which is consistent with the length of the laser cavity of 56 centimeters. Now, the first thing I'm going to do is see whether the polarization of all these laser frequencies is the same or not. So what I'm going to do is insert a polarizer in the beam, and then rotate the polarizer. In fact, let me up the gain a little bit here. And let me rotate the polarizer, or the transmission axis of the polarizer, to see whether the polarization is the same for all of them. And as you can see, I can extinguish all of them when the polarization is horizontal, and bring them all up when the polarization is vertical. And remember, this is the light that was plane polarized. So now we've shown that indeed all the frequencies that come out from this laser, all of them have the same polarization, the polarization in the vertical plane. So now let me take the polarizer out and readjust the gain on the scope. So back now to the three frequencies. You can see that they move around because the cavity is drifting in length due to the air currents or temperature effects or what have you. And even in fact, as I speak, or as I tap on the cavity, you can see that I can create a mess of the spectrum just by simply tapping. Or if I lean on the table, you can see again that I can make the frequencies wander around. Now, the fact that I have more than one frequency means there is enough gain for several frequencies to oscillate, due to the fact that the gain medium has some bandwidth, not very huge, but some bandwidth. Now, I can make the laser go at one frequency by introducing loss, by simply misaligning the cavity to introduce loss. So you can see here I've got only two frequencies, and in fact I'm going to up the sensitivity of the scope because the power goes down when I misalign. You can see here, I have essentially two frequencies, and if I add more loss, I can have only one frequency. So in a way, I can run this laser at one frequency, but it's difficult to keep the other one out. And then you can see that as I lean on the cavity, I can make this frequency move around. Now, generally, that's not a good way of getting single frequency, and we have other techniques for getting single frequency, which we'll discuss later. For this laser, it's best to align it for the highest power out, and this way we'll automatically get more than one frequency. And for a lot of applications, this is fine. All right. So to summarize, then, this laser that is 56 centimeters long, or the cavity is 56 centimeters long, then gives us about 3 modes, and the spacing between each mode is about 270 megahertz. And all the modes have the same polarization. Now we're ready to look at the other laser, the laser that has internal mirrors and also shorter in length. So when we come back, then we'll look at that laser. Now we're ready to look at the spectrum of this laser here with internal mirrors. The setup for looking at the spectrum is the same as before, but let me just remind you of it. Here's the output of the laser reflected by this mirror into the scanning Fabry-Perot cavity. The output of the cavity then goes onto the oscilloscope over there. Now, as you can see on the scope, and let me adjust the center of the scan, as you can see we have 2 big modes, and these are spaced by 680 megahertz, which is consistent with the length of the cavity, of the laser cavity of 22 centimeters, given by the 680 megahertz is given by C over 2L, the spacing between longitudinal modes. So these are 2 longitudinal modes of the laser. This little fella here is a 3rd mode that's coming in at an odd position because the free spectral range of the scanning Fabry-Perot cavity is not quite large enough, so we're getting a wraparound from another order. So let's not worry about this one too much. So let's look at essentially the 2 main longitudinal modes of this laser. Now let's look at now the polarization of these modes. So now what I'm going to do is take the polarizer, and as we did with the other laser, let's take the polarizer and look at the spectrum. Now if we look at the scope, after I make a slight adjustment of the gain because of the loss in the polarizer, now what I'm going to do is look at the spectrum of the laser light on the scope as a function of polarization. So first, you can see with the polarization set at this angle, you can see essentially we have predominantly one mode. And then if I rotate the transmission axis of the polarizer, I can extinguish this mode and bring up the other one. Now let me just center the mode on the scope so I can bring up the other one. You can see indeed I have single frequency operation on just one mode. So I either have this mode here, or if I rotate the polarizer, I can bring up the other one. So again, let me go back to the first one and then to the one over here. Now this is different from what we had with a laser with external mirrors and the Brewster windows, where we found that all the modes were the same polarization. Now here we find that one mode is one polarization and the other one is polarized orthogonal to the first one. And in fact this explains why the output of the laser wasn't plane polarized as in the external mirror cavity. Now this is very interesting, that because we have internal mirrors, the modes have orthogonal polarizations. At least adjacent modes have orthogonal polarizations. And in fact, this is a very easy way of selecting single frequency operation by simply placing a polarizer in the beam and then selecting one frequency. Now let's look at this single frequency behavior. If I want to tune the laser frequency, I simply blow some air onto the laser to, I blew too much. Do it again. So you can see that I can scan the laser frequency by simply changing the length of the cavity. In this case, I'm cooling off the cavity. Now, let me also point out that the line width that you see here is not the laser line width at all. The line width that you see here is determined by the scanning Fabry-Perot cavity. The line width, the true line width of the laser is very narrow. In fact, in principle, it's a fraction of a millihertz. But because laser jitters and what have you, you'll get a little broadening, but certainly nowhere near as wide as what you see over here. And again, let me bring up the other mode, the other polarization, and again, this one will also tune across the gain curve of the cavity. I mean, a gain curve of the medium of the laser.
Well, I hope you've enjoyed this demonstration as well. I think there's a lot to be learned, and as you know, it's a brief course. It's not too mathematical, so don't expect that you'll be able to answer all the questions just based on this course. But I hope that this will trigger your excitement, and maybe you want to go take other courses or maybe start opening up books. Now, there's still more to lasers. And now what I would like to get to is the is the optics of the laser beam, and that is you know, the shape of the laser beam that comes out from lasers. I'm talked a little bit about it before, and I'd like now to start talking about it. Again, I'm not going to get into the math because this is not the right course for it. All right. So forgive me if I don't convince you completely. But if you have any questions, please go ahead and ask it, and maybe this will give me an opportunity to explain a little bit better what I mean. So now let's turn to the optics of laser beams, and as I mentioned before, the shape of the laser beam is determined by the mirrors. If you have two plane mirrors, then the beam bouncing backwards and forwards here will be collimated, and if you leak it out here, it'll be collimated. If I had, let's say, a curved mirror and a plane mirror, then I'll have the beam shape inside the cavity will be something like this. Will be big on one side, small on the other, and then the beam leaving this mirror will also expand, just like it expands into here, will expand to the other side. So the beam will expand depending on what we call the waist of the beam. All right, now if you have two curved mirrors, let's say two concave mirrors, then the beam shape will look something like this, and again will expand coming out. But one shouldn't worry, because all you have to do, just like I showed before, with lenses, you can bring it back to any size you want. And for example, in this next demonstration that we're going to have, we're also going to do the following. We're going to put lenses at the outputs of beams, and we're going to demonstrate this region here for you. And in fact, we're also going to put an aperture here, and we're going to clean up the beam, because sometimes the lenses are not perfect, the mirrors of lasers are not perfect when the light goes through them, and there's all sorts of distortion. So by putting an aperture here, what we call spatial filter, we'll clean up the beam, and we'll have a very clean looking spot. So I think now we're ready for this next demonstration on the optics of laser beams. And here, all we try to show you is the shape of laser beam in a tank of water, because it's difficult to do that in air, to visualize the laser beam. Now, I want you to remember one thing. You know, I've been saying about how small the spot is and what have you, the focus spot. In this case, you're going to be limited not by the laser, you're going to be limited by recording resolution, and especially TV resolution. So please don't think that the beam you're going to see, the narrow spot of the beam you're going to see, is really what is that big. It's really much smaller than that, and it's a limitation of let's say, of this medium of television right now, that it looks big. But at least it'll give you some idea of what this beam looks like. So I think now we're ready. Let's look at this demonstration on various aspects of the optics of laser beams. The light beam from a laser is as close to an ideal beam as one can get. What I mean by that is that the properties of this beam, the propagation properties, are limited by fundamental laws of physics, for example, laws of diffraction, and not by the properties of the light source. For example, a laser beam from a well-behaved laser can be collimated to a very small angle. This angle is determined by, as I say, the laws of diffraction, which is the wavelength of the light divided by the diameter of the beam. And it doesn't say anything about the size of the source or the properties of the source. And that is the ideal collimation limit on a beam. At the same time, a laser beam can be focused to a very small spot. The size of that spot is again determined by laws of diffraction, which is the wavelength of the light divided by the diameter of the beam multiplied by the focal length of the lens. And if we choose the diameter of the beam and the focal length of the lens about equal, then the spot size would be of the order of the wavelength of light. And again, doesn't say anything about the physical size of the light source or what have you, as we would have in a case of an arc lamp or any other kind of light source. Now, in these demonstrations that follow, we're going to illustrate some of these basic properties of laser beams. What we're going to start with is this laser here, which is a helium neon laser, and here is the beam from the laser. We're going to reflect it by this mirror here, and then reflect it again by this mirror here, and let the beam fall on the screen. Now, you might be able to get a better feeling for the beam if I use the black card. Maybe the colors will come out better. So here is essentially the beam coming out directly from this laser. And it's very difficult to tell what's going on. It looks pretty collimated. Now, the first thing I'm going to do is expand the beam and see what it looks like. So I'm going to take a short focal length lens, and I'm going to place it in the way of the beam. And here on the screen now, we see the expanded beam. Now, if we go take a close-up, we can see that it's got rings and what have you. Now, these rings that you see, or these fringes, are due to the fact that the laser beam has to go through optical components, like the output mirror of the laser has to be reflected by these mirrors, and then has to pass through this lens over here. And they all corrupt the laser beam. But we can easily get rid of these effects by placing a pinhole. Here's the pinhole. And what I can do, I can just place the pinhole in front of this lens, or at the focus of this lens here. And if I have my adjustment right, I have then so-called the spatially filtered laser beam. As you can see on the screen now, we got rid of all these rings, and this is as close to an ideal laser beam as one can get. Now, what we see here is the speckle. So if I move the screen a little bit, you can see I can wash out the speckle. So when it's still, you can see the speckle pattern, because the surface is not smooth. But otherwise, you don't see any fringes on the beam. And also, there's an intensity distribution which is essentially Gaussian squared. The field is Gaussian, but the intensity distribution is Gaussian squared, so that essentially drops off to zero in the wings. All right, so this is a so-called spatially filtered laser beam, and for some experiments, it's very important to spatially filter the beam, especially in interferometry and what have you. Now, I'm going to before I do anything else, I'm going to show you that the placing of the pinhole is very critical. If we can now take a close up of the spot. Now, if I move the pinhole slightly, you can see that first of all, the beam disappears, because this pinhole is only of the order of about 12 microns or so. And another point that one has to watch out for when using such a pinhole as a spatial filter is that if the pinhole interrupts any part of the laser beam, now let's look at the inset again, that this Gaussian distribution in the beam gets affected, and you will start to see all kinds of diffraction rings. So again, for the spatial filter to work, the pinhole must not cut any of the essential part of the laser beam. Now, what I'm going to do is collimate this beam of light. And here, what I will use is a simple two-lens collimator, and I'll place it over here, And here it is. Here's the output from the collimator on the black card. You can see that obviously you can't check on the exact collimation, but you can see that the beam can be simply collimated. All right. Now the next thing that one sometimes wants to focus the laser beam. Again, if I take a simple lens and again place it in the beam, now I can focus. Let's look at the beam again. I can focus it to a tiny spot and back out again. Here we are. Let me focus to a small spot. Now, it's very difficult to see the size of the spot or even the shape of this focused Gaussian beam. Remember I said before they can be focused to a spot size of the order of the wavelength of light. And it's not so easy to see it on this card. So what we're going to do when we come back, we're going to get a water tank and pass the light beam, the focused light beam, laser beam, into the water tank, and we'll add some scatterers to enhance the scattering from the laser beam by the water. And then you'll see you get a better picture for the focusing of this Gaussian laser beam. So when we come back, we'll have that all ready for you. We have now placed the water tank in place so that we can pass the laser beam through it and visualize the laser beam as it passes through the water. We've also, here is the tank by the way, and we've also added a few drops of milk to enhance the scattering. And that's why the water looks murky. In addition, we've tilted the tank a little bit so that we can get a better angle for the camera. Now, the setup is just like we had it before, but let me remind you of it. Here's the laser, is the beam from the laser, reflected by this mirror here. Then we pass it through a polarization rotator here so that we can adjust the polarization for maximum scattered light for the camera. And then the output after the polarization rotator gets reflected by this mirror here into this short focal length lens, the spatial filter we had before, and then the collimator. The output of the collimator is here before it goes into the tank, and then out here after it leaves the tank. Now, in order to visualize the beam as it propagates in the water, we'll have to turn the room lights down. But let me tell you what I'm going to do when the room lights are down. I'm going to first look at the collimated beam in the water, and then I'm going to take this lens and another lens like this, and I'm going to place it over here so that we can focus the light into the tank. All right? So, and then we can explore the region around the focus. So now we're ready to turn the room lights down and look at the region around the focus by simply observing the scattered light in the water. Now that the room lights are dimmed and the camera focused into the tank, first thing we see is the collimated beam, or the scattered light associated with the collimated beam. There's not much I can really say about that. More interesting is when I put a lens before the tank and look at the focal region. Here we are. I'm going to adjust the position of the lens so that the waist, or the focused region, the focal region, is in the center of your screen. Now, the things that you can observe is that laser beam coming in from the left then is then focused to a region where the spot is small, spot size is small, and then expands again on the other side. Now, because of the limitation of television recording, and especially recording of color, especially red, you do better. If you want to see how narrow that focal region is, you do better if you turn down the color, turn off the color, and look at it in black and white. If you do that, you'll see that the focal region is now narrower than it is when it's red. But in fact, the truth is that you cannot really observe this way the true size of the focused spot, because that's only a few microns, and it's going to be limited by television resolution in any case. But at least you get a feel for the fact that the beam is pretty narrow at the focus. Another thing you want to observe is that the region around the focus is reasonably constant in diameter, and that's called the Rayleigh region, where the expansion of the beam is not so big. But after that, then the beam expands one side and then symmetrically the other side of the beam. The intensity distribution, if I take a slice anywhere along the beam, the intensity distribution is still Gaussian or Gaussian squared. The field distribution is Gaussian, intensity is Gaussian squared. The other thing to observe is that the curvature. Now, at the focus, or at the middle of that Rayleigh range, what we call the focus or the waist of the beam, the radius of curvature is infinite, which means that we have a plane wave. Now, it stays plane within the Rayleigh region or close to plane, and then we develop the curvature. So we have an expanding beam on one side, an expanding beam on the other side. And in fact, if we go far away, the radius of curvature is the same as if we had a spherical wave starting at the waist. All right, that's with this lens. Now I'm going to take this lens off and place another lens that is a little shorter in focal length. And here we are. Oh, let me turn it around. And then let me again center it so that you can, the waist is the middle of your screen. You can see now the divergence is different, showing that it's a shorter focal length lens. Now if I move it to one side, you can see that the beam gets quite big very quickly, and also the same to the other side. And then but the other thing you notice is that the Rayleigh range, or the region around focus, now is smaller. So it's a tighter focus than in the previous case. And as the focal length of the lens gets bigger and bigger, then the Rayleigh region gets bigger and bigger also. So here we are with a shorter focal length. And again, if you want to see a nice small focal region, then you want to turn down your color and look at it in black and white.
Well, now you can say that you know all about the nice things about a laser. In this next part, I'm going to start telling you about sort of problems and other issues about lasers. In fact, I call it other issues and problems relating to lasers. The first one is, and again, without doing any math, I want to tell you about amplifier limitations and what can go wrong in amplifiers. All right, so here we go again. We have our three-level system, which is the simplest of amplifiers. We have the pump, and then we take some of these atoms from here, put them up here, and we have a population difference. And if there were no lasing, as we mentioned before, these atoms here would drop down to level 2 and through spontaneous emission, just like over here. So if you just leave the amplifier alone and there is no cavity, let's say, then what happens is that the atoms will drop by spontaneous emission
and there will be no, and then they all, after a while, will all drop down by emitting spontaneous emission. If there is a cavity and spontaneous emission gets the laser going, then what's going to happen is that these atoms will be driven down by stimulated emission. Now, as you can see, as you drive these atoms down, they're going to go to this level 2, and we have to know what happens to them when they're in level 2. If the atoms can't get out of level 2, then as you can guess, sooner or later, level 2 is going to have more atoms in it than level 3. And as we know, that's a no-no in lasers. That means it becomes absorption here, not gain, because N lower now is bigger than N upper, so we have a problem on our hands. So this laser then will become like a pulse laser, because you start with gain, a lot of gain, and if you laser, you will laser for a short time until the populations are equalized, and then boom, the laser goes out. So the question now is, well, what do you do about it? If indeed level 2 starts to fill up and won't go down. Again, you have to solve that problem. So what you do, you have to come up with a way of making this level here decay down, either through spontaneous emission by choosing the right system, or maybe by adding other gases or what have you through collisions to bring this level down by collision. There are many tricks, and so a continuous laser then has to have a mechanism for getting rid of this bottleneck of this level 2. It has to bring it down so that, and it's got to be fast, much faster than these things coming in, because otherwise then this is going to build up, and you have, just like backing of water tanks, it'll just back up, the water will back up and will not go away. So the key thing here is that to make the relaxation time here, what we call gamma 2-1, which is 1 over the effective lifetime between level 2 and 1, to be bigger, gamma 2-1 has to be bigger than gamma 3-2, which is 1 over tau 3-2. So in order to maintain N3 minus N2 as something positive, more than 0, in the steady state, then we need to have this gamma 2-1, this decay rate here has to be faster than the decay rate into level 2. The rest is constants, is like N1, the number in the lower level, plus the power in the pump, and so on. But basically the key things are that these relaxation rates, that this one is bigger than this one. If not, then essentially you get a pulse laser. And as we'll see later, in different amplifiers, this is taken care of differently. All right, so obviously this is a problem that you've got to worry about. That's why you don't make anything laze. Some materials make better lasers than others. All right, that's about one of the problems in amplifiers. Now let me talk now about something even more basic. Okay, and that's about cavities, where cavities can go wrong. So my topic here is on cavities, and so far we've talked about cavities with curved mirrors, and but we haven't said anything about the spacing between the two mirrors. If let's say these are two concave mirrors and I bring them close, then the mode inside will look something like this, a little fat waist here. If I pull them apart a little bit, then I begin to get a mode that looks like this, with a waist here that is smaller. And also, I'm not really doing it here because I'm not going into the details, but basically the curvature of the field inside the cavity at the mirror is the same as the curvature of the mirror, so that you can get reflection back again. All right, so we're not really going into that in this course. Now, if I pull the mirrors even further apart, I see that I create this waist here, which is very small. It's about this small. It becomes very small, much smaller than I've had it before. Then what happens when I pull the mirrors even further apart from that condition? All right. So let's see what happens in this simplified version. Well, this is what's going to happen. If I pull the two mirrors now further away than in here, then what happens is the light starts to walk out, will not be contained inside the cavity. because what's nice here is the light's getting refocused back into the cavity and is going backwards and forwards without leaving the cavity. And it's all in all these cavities. But here, I exceeded some rule, and the light will start walking out, which means now in order to make this laze, I have to have much bigger amplifier to overcome this loss. Usually lasers will quit lasing unless you have a very high gain medium here. And this is called the unstable, so-called unstable resonator. All these others are stable, we call stable resonators, and unstable. I know I haven't used many formulas in this course, but here is one. Here's a simple one. I'll give it to you. So this is in terms of the radii of curvature of the mirrors. This is rho 1 and rho 2. And they can be concave or convex. If they're written for concave, but if any of the mirrors are convex, then you have to change the sign. L is the separation between the two mirrors. And this little formula here tells you when the cavity is unstable. It turns out the cavity is unstable when 1 minus L over rho 1 times 1 minus L over rho 2, the product of these two quantities, is if it's between 0 and 1, then the cavity is stable. If it's outside that, the cavity is unstable, and this is one example where the cavity is unstable. So you can have the best mirrors, you can have the best amplifier, but if you don't have the alignment right and the length separation right for given curvatures, the laser will not oscillate, and people think you don't know what you're doing. But all you have to do is go back to this formula and make sure that you stay inside it. So that's a problem common problem with resonators. And this also tells you, this formula also tells you whether you can use convex mirrors. And it turns out again, in certain conditions, you can use a concave mirror and a convex mirror. But to use two convex mirrors, that's a no-no, because that will not satisfy this condition. As I say, if you're more interested, then you have to consult the literature. Now, I'd like to talk about the spectrum of a laser in more detail. Now, before, we said that the laser will be single frequency if you have only one mode under the gain curve. And if you have more than one mode, then you have more frequencies, at least the possibilities of more frequencies oscillating. Now, a lot of applications can't tolerate more than one frequency. For example, communication, interferometry, holography, and a lot of sensors, they cannot tolerate more than one frequency. But so for some other applications, it's fine, like materials processing, medical applications, CDs, and so on. More than one frequency is okay. So now let's see how one can select a single frequency from essentially a multi-frequency laser. Now, in the demonstration, we showed you that all these modes can happen, and we showed you that if we lower the gain or misalign a little bit, we can bring the gain down so only one mode will oscillate. But that's not a smart way of doing it, because you lose a lot of power output. So the idea here is to have how do you have a long laser, right, with lots of possibilities, lots of modes, a lot of gain in there, and only select one frequency out of that. That mess of frequencies. Okay, so let's see now how we might do it. So this section then is on the single frequency selection, and I remind you again of having, let's say, a long cavity here with a long gain medium, and I have lots of modes under the bandwidth of the amplifier. Here's my loss line. So all these modes here will oscillate, and you can get all these frequencies. So the question here is, how do I select then one of these frequencies and not all of them? Well, there are many ways. The most common way is what we call an echelon. We place this shorter cavity within the long cavity. Again, over here we have the modes of the long cavity, where there's all space C over 2L apart. And for the short cavity, the length is A, so the modes are spaced for this it's a piece of glass or two mirrors that are parallel. And the spacing is A, so the mode spacing is C over 2A for this short one. So now the whole idea is to couple the mode from this cavity, like this one here, with one of the modes from the long cavity, which is over here. And when they're coupled, when they're perfectly coupled like this, then only at this frequency will I get enough gain to overcome the loss. in the cavity, and the laser will oscillate over here at this frequency, which is determined by the overlap of these two, product of these two. Now at any other frequency, while before they oscillated, now they see this loss because of this, because you're off resonance with respect to that cavity, so the transmission is low, and then they will not oscillate. So only the overlap between the short cavity and the long cavity, then you will get enough gain to overcome the loss, and then you'll get lasing. At any other value, you don't. So this is a way of selecting single frequency. Now, if you don't like this frequency, you want some other frequency, all you have to do is you tune this little cavity, either by rotating this or by adjusting the distance. So you can move this resonance around, and you can select any of these modes you want. If you want somewhere in between, then not only you have to tune the short cavity, but you also have to tune the long cavity. And then this is, as I say, this is a very popular way of getting single frequency, and it's used quite a bit. It's a pain in the neck to put things inside the cavity, because any loss then will start cutting your gain down, effective gain, and your laser output power will drop. But this is a convenient way of getting single frequency. So you don't have to worry about the fact that lasers can put out many frequencies. There are techniques to select only one and to be able to tune that. Now let me talk about other problems with lasers, and that is the frequency and intensity variations. And then we'll do that very briefly, because one begins to think that lasers are always ideal. They're not. Let's go back to our simple picture of a laser, and here's the gain, here's the cavity mode, and here's the oscillation of the laser. Now, what determines this frequency? Well, as we've seen from way before, we saw that it depends on this integer q, which is the number of half wavelengths between the two mirrors, multiplied by c over 2l. So it certainly depends on L. So if L changes here, then the cavity mode will change, and of course we'll pull the laser frequency with it. So that the laser frequency can move around if the cavity moves around. And then a simple expression here for delta F over F, the change in the frequency over the frequency, is simply the change of the length of the cavity, or what we call the optical length, because if there's a refractive index here, that will change the physical length, because you have to multiply by the refractive index, divided by L. So then the change in the frequency, the fractional change in frequency, delta F over F, is the same as delta L over L. So if you want good stability, you have to keep delta L over L small. The other thing is the intensity of the laser. What determines the intensity of the laser, and does it stay constant? Well, we know that the amplifier, of course, determines the intensity, but the change in intensity will depend on the pump. If the pump here changes whatever it does to the medium, if it changes magnitude, then it's going to change the intensity. Or if you misalign, as we showed you in the demonstration, if you misalign one of the mirrors here, you will get more loss, which means that you need more gain to overcome the loss, which means the intensity will drop, and so on. So there are many ways of reducing laser intensity. So to keep it constant, all right, to keep delta I over I small, then you need to keep an eye on all these effects. Okay, and I think this is brings me to the end of this session. In the next session, we're going to talk about another property of lasers, and that's associated with transverse modes. These are when you look at a laser that's oscillating in transverse modes, instead of seeing the single spot, you see many kinds of many spots, and that for some applications is a no-no, and you've got to get rid of them.